My God, where am I now? But I did observe a fascinating, tragic creature. The modern university of scientifically known as Homo sapiens academicus. In order to survive this semester, he must complete his assignments by observing on his nesting habits. He has chosen a rigid, unforgiving chair and a flat, glowing slab. A fatal mistakes. Let's take a closer look at the anatomy of this creature distress. I know I was never to interfere with this nature, but looking at that spinal curvature, I just cannot simply stand by. We must offer him the help and tools of evolutions.
From an evolutionary biomechanics perspective, the human spine was simply not designed for this level of static loading. By extending his head so far forward, the moment arm on his cervical spine is massive. The muscles and ligaments at the back of his neck are fighting a losing battle against gravity to hold up a 5 kg head.
If we analyze his survival odds using the rapid upper limbs assessment, which is rural, the extinction is imminent. Look at the cervical trunk flexion and neck extensions. The shoulders are rounded and the wrists are bearing weight. This yields a critical rural score of 7. Without interventions, musculoskeletal disorders are inevitable.
First of all, you have to move his chair forward a bit.
Nice.
So next, we have to lower his chair a bit. So now, let's straighten up his back. Let me pull a bit. Okay, so now the laptop here, I think we need to add some height on the laptop. So there we have some supports. As you can see, now the keyboard is a bit too high, so I think we're gonna have some additional tools, yeah?
Notice the application of anthropometry here. Instead of the organism contorting to fit a hostile environment, the environment has been adapted to fit the physical dimension of the organism. The screen height now matches his eye level, preventing cervical strain.
Evolutionary leap is evident in the new ruler assessment. Green lines are drawn over the new angles. The neck is in a neutral posture, the trunk is upright and supported, and the elbow rests safely at a 90-degree angle with the external keyboard. The ruler score has dropped to a 2. This is a sustainable, low-risk posture built for long-term survival.
Finally, he thrives and he adapts with his biomechanics in harmony. He might just survive to see his graduation. Nature is truly magnificent! Why? Did I just apply my human figure in my dream? Oh my god!
In this presentation, I will explain the anthropometric evaluation of a laptop workstation setup. The focus is to compare the user posture before and after a makeshift ergonomic improvement. The analysis uses body measurements, workstation measurements, and a simple ergonomic comparisons to identify what improved and what problem still remains. The first issue is the original laptop workstation. From the photo, the user was leaning forward and bending the neck downward. This happened because the laptop screen was too low compared to the eye level. The chair was also slightly too high compared with the user property height. Because of that, the legs were not in the most comfortable positions and the feet did not rest naturally. Overall, the workstation dimensions did not fully match the user body dimension. This slide summarizes the key data used in this calculation. The user has a stature of 169 cm and a poplite height of 47 cm. The chair height changed from 51 cm to 46 cm. The screen center height increased from 92 cm to 112 cm, while the viewing distance increased from 50 cm to 60 cm. These values were then compared to determine the ergonomic mismatch before and after the makeshift improvement. The first result is chair height. The user poplite height is 47 cm, but the original chair height was 51 cm. This means that the chair was about 4 cm too high. After the adjustment, the chair height became 46 cm, so the mismatch was only about 1 cm. This is more suitable because the feet can rest more naturally on the floor and the lower limbs are better supported. The second result is related to the screen. Before the adjustment, the laptop screen center was 92 cm, while the user eye height from the floor was 111 cm. The vertical difference was 19 cm, which explains why the user bent the neck downward. After using the stand, the screen center increased to 112 cm while eye height was 120 cm. The mismatch reduced to 8 cm and the viewing distance also improved from 50 to 60 cm, showing that the user could sit further back in a more upright posture. However, the improvements also introduced one important issue. The laptop stand raised both the screen and keyboard. Before the adjustment, the keyboard height was 75 cm and the elbow height was 69 cm, so the difference was only 6 cm. After the adjustment, the keyboard became 95 cm high while the elbow height was 73 cm, creating a 22 cm mismatch. This can also cause shoulder elevation, arm reaching and wrist extension. Therefore, a laptop stand alone is not enough. Hence, external keyboard helps to reduce the difference between the elbow sitting height and keyboard height to 2 cm. In conclusion, the makeshift intervention successfully improved several ergonomic factors. The screen height became closer to eye level, the user could sit more upright, and the chair height was more suitable for foot support. However, the keyboard became too high after using the laptop stand. Therefore, the best recommendation is to keep the laptop stand for screen elevation, but add an external keyboard and mouse at desk level. With this arrangement, the neck, back, shoulders, elbow, and wrist can remain in a more natural and neutral posture.
The biostatic mechanics analysis of a laptop workstation. The objective of this study is to evaluate the forces and moments acting on the lumbar disc, which is one of the most heavier loaded regions of the lower back during prolonged sitting. The comparison is made between a makeshift workstation and an improved workstation. A free body diagram was developed for biostatic mechanics analysis. The lumbar disc was selected as the pivot point. The force acting on the body include the upper body weight, muscle force generated by the spinal muscle, and the reaction force acting at the lumbar spine. The upper body, consisting of the head, arm, and trunk, was modeled as a single rigid segment with a mass of 40 kg. Using the equation W equal to mg, the weight of the upper body was calculated to be 392.4 newtons. Since the user remains stationary while typing, the body is assumed to be in static equilibrium. Therefore, the conditions of equilibrium are that the sum of forces in the horizontal direction equal to 0, the sum of forces in the vertical direction equal to 0, and the sum of moment equal to 0. The lumbar moment is calculated using the equation moment equal to force multiplied by distance. From the comparison shown, the makeshift workstation caused the user to lean forward towards the laptop. The workstation measurements show a screen height of 92 cm and a viewing distance of 15 cm, resulting in a large moment arm of 0.25 m. After economics improvements, the screen height increased to 112 cm and the viewing distance increased to 16 cm. This allowed the user to maintain a more upright posture, reducing the moment arm to only 0.12 meters. A smaller moment arm means less torque acting on the lumbar spine. For the makeshift workstation, the lumbar torque was calculated as 98.1 Nm. To balance this moment, the spinax muscle was required to generate a force of 1962 newtons. This results in a total spinax compression force of 2354.4 newtons acting on the lumbar disc. For the improved workstation, the lumbar torque decreased to 47.1 Newton meter. The required muscle force was reduced to 942 newtons, while the spinal compression force decreased to 1334.4 newtons. This result shows the improving workstation posture significantly reduced biomechanical loading on the lower back. In summary, the improved workstation reduced the moment arm from 0.25 meter to 0.12 meter. This results in a 52% reduction in lumbar torque, a 52% reduction in muscle force, and a 43.3% reduction in spinax compression force. The result clearly demonstrates that the forward-leaning posture in the makeshift workstation creates substantially higher loading on the lumbar spine. Therefore, proper workstation design is essential to minimize the biomechanical stress, reduce muscle fatigue, and lower the risk of developing musculoskeletal disorder during prolonged computer work.